So this morning I thought I might show you a large off-grid system that we've completed here in the Southern Highlands of New South Wales. Right here you can see a 70 kilowatt solar array, ground mounted array, which is providing the renewable resource for the project. Now everything's been installed in this container. It's quite a long container, it's a 40-foot container. In one end of the container we have, down here we have a backup diesel generator. It's separated by a wall, and then in the other end of the container here, in this section, we have a all the batteries and the inverter equipment. You'll notice here there's just here there's a cable ladder, and that's the cables that come up from the array that I just showed you. They come up underground in conduits, and they come up just in under here, come up into the cable ladder, and then into the inverters, which are inside, which I'll show you in a minute. It's very important to protect string cables, because in this case the voltage is up over 800 volts, which can be quite hazardous. So it's very, very important to provide signage on equipment like this, and also to keep it protected so it can't be damaged. Incidentally, you'll notice we have an earth stake outside as well, because you've got to remember we're basically providing a small power station here for the consumer, for the customer. He also has a very large diesel fuel tank, which we don't expect to use much of, but in the winter, when they have a lot of heavy usage going on here at the property, may be used in the future. Here we have, inside here, this is where the backup diesel generator is. It's quite a large generator. Normally, this is about 180 kVA, but normally you wouldn't need anything quite so big, but this site has some fairly significant loads at different times of the year, so it may be called into use. So we'll just go around to the battery end of the container. So everything's installed in this container, which also has an additional roof over the top, just to help protect the container, but also to help keep it cool. Another thing, on the doors, you'll notice there's quite a bit of signage that's required by Australian standards, just to warn people of the hazards going into a room such as this. Now this room's actually also air conditioned. We have an air conditioner at the end, because it's quite important to keep equipment like this cool if possible. So on this side of the wall, you'll see these are the MPPT inverters, and the string cables which you saw outside. They all come into these string fuse boxes. So each string has a fuse on it, and if you've been designing systems, you'll understand why. And then the DC side comes up into the inverter. The inverter has AC cables then that go from here, and they go out and they go up into the PV distribution board. So that's the MPPT side. And this is where we're getting our renewable energy resource coming into the system and providing the energy to charge the batteries. Now on this side here, this is what we call a multi-mode inverters. Each of these inverters, this is 20 kilowatt inverter, 20 kilowatt inverter, 20 kilowatt inverter. So basically over 3 phase we have 60 kilowatts of AC power that can actually go into the site at any one time. In fact, it could go up to 80 kilowatts if it needed to for about a half an hour, because good inverters always have a fairly significant surge capacity. And so in this case, when you do this kind of configuration, One of the inverters is the master inverter, and it's generally phase A. So this is our master inverter, and these are what you might call worker inverters. Underneath each inverter, each inverter, you'll notice down here we've got what's called a DC isolator. So these inverters are converting the DC volts from the battery, converting it into AC volts, alternating current volts, at, in this case, 240 volts at 50 hertz. So the first one is, 240 volts, 240 volts, 240 volts, but between them, remember, with three phase, it'll be 415 volts. Okay, so each inverter has its own DC isolator. Those DC isolators are rated at 250 amps. Okay, then the cables come down from the DC isolator, then they come along, and they come into these fairly significantly sized isolators. They're quite big. Each one of those is rated at 630 amps. However, we've got them wound back to 400 amps each. And so we have two DC isolators here because, let me just open the box, because we have an isolator for each battery string. There's actually two battery strings here. So that's what it looks on the inside. So this is the active of one battery string, and this is the negative of the same battery string. Interestingly, these type of DC circuit breakers are designed that the positive comes in one side, goes up, goes across, and comes out, as part of the design to be able to operate at the full 630 amps if required. Then this DC isolator also links on the load side of the isolator down the bottom here, so that they're all actually part of the same DC bus. However, on the line side, meaning the battery side, each isolator goes to a different battery stack. And when I say battery stack, these are the batteries. So there's actually 6 battery stacks here, meaning that there are 3 battery stacks for each string. So each battery stack is rated at 48 volts, and when we put a stack in series, 3 of them in series, we end up with about 160 volts, which is what this system is designed to operate at. These batteries are probably a little unusual to you. They're still a lithium ion battery, but they're actually a lithium ion titanate. Most of you will be familiar with lithium iron phosphate batteries, but these batteries are quite different. The chemistry is quite different. And the major point of difference with these batteries is that we'll get 22,000 cycles out of a battery kit made of lithium titanate, but battery kits made of lithium iron phosphates that you're probably more familiar with, you get somewhere between 5,000 and 7,500 cycles. So there's a significant difference with these batteries. However, they are significantly more expensive. The biggest advantage is, though, at 22,000 cycles, if you multiply the cost of the batteries over the cycles, you'll find that they're very economical battery. However, the upfront costs are very high. Now, a really important thing you need to do when you wire batteries is that the cable lengths need to be the same. So it's very important because of an issue called voltage drop, where you can lose volts over the cable length. You probably would have learned about that before, simply because the power losses is, the formula is power losses equal I squared R, and anything squared in a formula becomes an exponential, uptick. And so you've got to be careful that both battery strings, the cable lengths are the same, so we don't get any mismatching when it comes onto the DC inverters. On the DC bus side, we want each string to be equivalent in voltage. We've actually tested ours and we're about 0.1 or 0.2 of a volt away from each other, away from each string, outside of each string, which is quite tolerable. But if you had a few volts, it may not be so good. And so these batteries are quite unique. Down below, down here, we can see these are what we call the battery controllers. And what these are doing is they're connected to these battery management systems on the top of each stack, like there, and they're all wired back into our collection device here. And what this is designed to do, these two cables here, it's designed to actually trip out. Here we are here. It's designed to actually trip the circuit breaker off, so that if there's a fault or if there's some unsatisfactory condition in the batteries, it'll actually trip the circuit breaker off, to provide safety. If we look at these 6 batteries, remember I said that we needed to keep the batteries cables the same length. So if we had just brought all the cables to the first 3 stacks, there's 1 stack, 2 stack, 3 stack, and then we'd wire the other string in number 4, 5 and 6 stack, the battery cables would have been considerably different in length. So what we did was we brought the cabling to the first battery, then we skipped to the third battery stack, and then we skipped to the fourth battery stack. And so in other words, we ended up with battery stack A loops to A, which loops to A, and battery stack B, which is the second stack, loops to B, which then loops to B. And so that was just a clever way to keep the cables all the same length. So if we go back to the PV distribution board, here I'll just open that up. Just get that open. So inside here we have the circuit breakers for each inverter. Then we have a main switch, and then the cables come up out of the distribution board and they flow into the main board, which we'll go to in a minute. Then we have quite a few cables coming back from the main board, which come back and connect down into our multi-mode inverters. I have a wiring diagram which will make a little more sense if I show that to you. So all the energy at the moment, you could probably actually hear these Phoenix inverters working. It's only early morning here, but already on one of them, we have 12 kilowatts, 14 kilowatts, and 13 kilowatts. So they're already putting quite a bit of energy and supporting the site load and simultaneously charging the batteries. And I know they're charging the batteries because if I look here on the front face of the inverter, I can see that the charging source is the renewable energy source. If the generator was operating because it was a cloudy day or we needed additional energy, then we would see a little light on here, which would be the charging source, would be the AC side. Then we'll go to the main board. So as I said, all the energy at the moment is flowing from the PVDB and coming over into the main distribution board, which is here. So we designed this board and had it made by a manufacturer. It's a specially made distribution board, and you'll notice that up the top here we've got the solar inverter distribution board. This goes out to the site, and we've got the inverter, the Cellectronic inverters. So all the energy that comes from the multi-mode inverters, it comes into this circuit breaker here and feeds onto the bus bar. All the energy from the Fronius inverters, which are the MPPT inverters I just showed you, and coming along these cables here, they end up on these, on the bus bar through this circuit breaker, and exiting this switchboard, going out site distribution. This goes out to the site. This here is the main circuit breaker that comes from the backup diesel generator. So if we need to have any additional support from the generator, it comes in through that circuit breaker. Now inside this board, just open it up for you. You've got to be very careful whenever you get into a switchboard. Okay, so now you'll see we have the cables coming from the generator, which come into this main switch here, out of the top of the main switch, and they come down and they come through a circuit breaker here. Sorry, not a circuit breaker, a contactor. And there's other controls in here, but I won't get too deep into that. But this contactor always remains open, and the contactor is then connected to the bus bar up here, right? And everything's connected onto the bus bar. So you call this an AC coupled system. So what happens is, if the multi-mode inverters, if the programming calls for a generator, the generator will start, and so it becomes live on this side, becomes live on the line side of the contactor. There's some sensing devices that then they inform the multi-mode inverter that there's power there, and then it begins to synchronize. So we have to have a synchronization between the inverters that are operating and putting energy into the site, and the generator. The sine waves need to synchronize. If they don't synchronize, you'll have a bit of a disaster here. And so when the generator is called, we can hear the generator switch on. We know there's power because we get a little signal over at the multi-mode inverters. And after about 5 seconds, there's a synchronization going on. Then you'll hear this big contactor come in. And so what happens then is the generator is then supplying power onto the AC bus. The inverters are supplying power onto the AC bus, and also the multi-mode, the maximum power point tracking inverters, the Fronius inverters, they're also supplying power onto the DC bus. So that's basically what it looks like inside a switch. This is a fairly sophisticated board for an off-grid system, but it's what was needed in this case. We've also just got a small distribution board for this site, and we also have some control equipment here, because we're also able to extract data out of the multi-mode inverters and match loads on the site. Now, as with any installation, you need to be providing signage and also wiring diagram. So for example, this is the wiring diagram for the site. So if someone else comes in here and they need to understand what's going on, basically they'll see everything here on the wiring diagram. So for example, there's our Fronius inverters, which are, that's those guys there. You see them here on the drawing. So if you trace them out, we come into the PVDB, which is our PVDB here. And then the cables that come out of the PVDB, that's them there. We've got our generator cables coming into the main switchboard, which I showed you a minute ago. They're actually underneath here and going into the generator room behind us. And there's our Cellectronic 20 kilowatt inverters, which again, that's those inverters there. There they are there, and if you trace their cables out, they also come over into the main distribution board there. There's their isolators under each of the Cellectronic inverters. Then we also have Our controls also, we've coloured those just to make it a little easier to understand when you're here on site. So we have CTs, they're actually current transformers, measuring the current coming from the generator, and also sensing any backflow so that they can, if there's any backflow coming from the solar array here and trying to find its way back into the windings on the generator, the Cellectronic inverters, which are our multi-mode inverters, they would actually ramp these down so that we don't have backflow issues. And then we've also got, that's that big contactor I was showing you a minute ago. Oh, sorry, there it is there, that big contactor I was showing you a minute ago. And it's pulled in and out by a small relay which is there. So the controls do get a little bit sophisticated and they take a little bit of understanding and some experience, but it's all achievable. And so I mentioned CTs a minute ago. If you look carefully in under the switchboard, you see those little yellow things there. That's the current transformers, the CTs, and they're measuring the current coming to and from the generator, and that's them there. So a well-constructed single line diagram like that can be very useful to someone coming to a site who needs to understand what's actually going on here. The other thing too is you'll learn over time is good cable management. Makes a difference to any project and keeps everything neat, tidy, but also provides mechanical protection to cabling in a plant room, and also provides protection to the people who may come and work in the plant room. But this particular system also, we have internet access, so there's a little device here called a Select Live, which is connected to the main inverter, which goes out through the internet there, which is connected to comms panel in the back there. That gives us access into this system at any time. So from my office at Smeaton Grange, I can look at this site, which is about 150 kilometres away. I can look at this site at any time. I can make any adjustments. I can see what's going on. I can see how much energy is being used. I can see the state of charge of batteries. I can manipulate it, make some changes, anything like that. Anyway, that's what a well-constructed off-grid system should look like. Albeit though, this is quite a large one for a large estate. Normally not quite as big as this, but this will give you a pretty good idea of what a good system might look like.